Aloha friends, let us do our water balloon analysis activity together. So on my iPad I have both the videos of my good catch as well as my bad catch. Now we are going to use video physics, but we aren't going to use it in the way that we have in the past. Since we have a slow motion video, we're not actually able to plot the water balloon with very much accuracy in terms of the data that video physics would give us. However, we can use video physics to figure out some basic information about our catch. So open up video physics and create a new experiment. Here you can see I already have my video of my good catch loaded into video physics. Now you will have to advance the slider at the bottom so that you can get to the moment just before, or just at rather, where the balloon touches the hand of your catcher. So remember, we're always talking about the frame of reference of the collision. So we only want information from when there is a force on the balloon by the hand. We don't want any information about the balloon in free fall. We don't want any information about the balloon being tossed in the air. We're looking at the delta T and the change in velocity from the time at which the balloon is in contact with the hand. So once I'm in approximately the right spot, I can see the balloon is just about to touch Tate's hand. I'll use the incremental buttons, which is the one in the circle, to advance my video frame by frame until I see the balloon just come into contact with Tate's hand. So I believe it's right here at this moment. Just before, I don't think the balloon has touched his hand, and just after, it's a little bit too far in his hand. So I think right here, this will be the moment that I start from. So use your best judgment in order to pick your starting frame. Now from here, and this takes a little bit of work, you'll have to tap on the frame counter, which is the one in the circle with the arrow, to count how many frames it takes your catcher to bring the balloon to rest. So you're basically counting the amount of frames that your catcher takes to stop the balloon. So here I'll do quite a few frames for you just as an example. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 30. 1, 2, 3, 4, 5, 6, 7, 8, 9, 40. Now I've already done this beforehand. And so for this catch, I decided that it took Tate 83 frames. Remember, this is in slow-mo. It took Tate 83 frames to change the momentum of the balloon from some non-zero amount to zero, basically to bring the balloon to rest. Now in my activity, you can see here that I've got some notes for myself. So we won't actually be using the timestamp on the video because we decided to use slow motion. So I've just crossed that out. But here for my notes, I see that for the iPad Pro model that we are using, the iPad films in slow motion at 240 frames per second. The data that I have from my good catch is that it took Tate 83 frames in order to stop the balloon. Now if the iPad films at 240 frames per second, what that means is that every second the iPad gathers 240 still images. So each frame is going to take or represent 1/240th of a second. Therefore, I can use these values to calculate the delta T for the good catch. Tate's good catch took 83 frames, and each frame is 1/240th of a second. So using some stoichiometry, I can multiply 83 frames by 1/240, and I see that delta T for the good catch was 0.35 seconds. So the amount of time it took Tate to bring the balloon to rest, or to apply a force to stop the momentum of the balloon, was 0.35 seconds. Now I haven't yet done this for the bad catch because I don't want to show you everything on this video and I want to leave some things unknown. But I can make a prediction that the delta T for the bad catch should absolutely be smaller than the delta T for the good catch. And that's because, as we talked about in previous class sessions, the bigger the delta T, the more we can maximize delta T, the smaller the force is required to change the momentum. So the longer it'll take Tate to stop the balloon, the less force on the balloon it will require. Therefore, for the bad catch, which pops the balloon, I would expect that delta T would be very, very small and that the force would be very, very big. Now, there's not much to do in this activity as far as analysis, so the only thing I ask is that you figure out delta T for the good catch and the bad catch, and that you come to class ready to answer these questions. Summarize your observations about force and time with reference to catching balloon as follows. A smaller or greater blank results in a smaller or greater blank. And the second question to think about before coming to class this week is, how does extending the time of a collision affect the required stopping force? And although that might seem mundane, and I know that you feel that we've gone over this quite a few times, but really just mull over it in the next 24 hours and let that root itself deep into your mind before we start our larger experiment this week.